Ever wondered what happens inside the multi-billion-dollar factories that create iconic fighter jets like the F-16 and the state-of-the-art F-35? Join us on an exclusive journey as we unveil the secrets of precision engineering and groundbreaking technology in the world of military aviation. The development and early production of the F-35 benefited significantly from the phased adoption of a digital thread philosophy. This approach involved designers creating 3D solid models, optimizing them for factory automation, and ensuring seamless integration with downstream manufacturing and sustainment processes. Recent technological advancements have enabled rapid validation of the as-designed to as-built configuration through the use of laser scanning and structured light technologies. It's worth noting that the term digital thread is said to have originated from collaborative efforts between the Air Force Research Laboratory (AFR) and Lockheed Martin during the early stages of F-35 development. In essence, Lockheed Martin defines the F-35 digital thread philosophy as the continuous creation, utilization, and recycling of 3D models by engineering and other downstream functions, such as manufacturing and sustainment. In Phase 1 of implementing the digital thread philosophy for the F-35 program, a comprehensive shift towards 3D engineering models and 2D drawings was undertaken by the engineering team. These detailed models, alongside partner and supplier contributions such as 3D tool designs and specifications, were seamlessly integrated into a shared product lifecycle management system. This allowed for easy access and configuration integration. Manufacturing in parallel adopted 3D models to design tools and factory layouts, streamlining facilities development and installation processes. Engineering leveraged the digital thread to create reduced dimension drawings for many airframe components. This not only reduced engineering costs, but also simplified supplier NC machining. Composites manufacturing, a critical aspect of the program, relied on the digital thread for fiber placement. Solid models play a pivotal role by incorporating inspection points for coordinate measurement machines, ensuring master engineering data accuracy. These 3D models served multiple purposes, from virtual mock-ups to manufacturing and sustainment simulations. They significantly curtailed the need for engineering and tooling changes compared to historical standards, thanks to their precise surface representation and improved part integration. Before we continue, let's have a little aviation humor. Did you hear about the aircraft that applied for a job? It had an impressive resume but couldn't land the position. Now, if you haven't already, hit that subscribe button to stay updated on our aerospace and aviation content. Phase 2 of the digital thread transformation in the F-35 program focuses on harnessing engineering data to support factory automation, resulting in substantial improvements in efficiency and quality. One prominent example of this automation is automated drilling, which is employed by all F-35 partners. Approximately 20% of all holes, including a remarkable 80% of accessible outer mold line (OML) holes, are now drilled using automation. This automated drilling process is approximately 4 times faster than manual drilling, delivering near-perfect quality and exceptional repeatability. Lockheed Martin utilizes automated drilling for various components, including wing boxes, forward fuselage skins, upper skins to center wing skins, and even the center wing assembly in Marietta, Georgia. Northrop Grumman employs a metrology-assisted robot for drilling narrow inlets on the F-35, while BAE Systems utilizes high-precision machining centers to drill its empennage skins and structures. This precision machining is especially impressive considering the tight tolerances required for bolt-to-hole compatibility. There are ongoing plans to expand the use of automated drilling further, aiming to reduce costs and enhance quality in a continuous effort to improve the F-35 program. Additionally, other forms of automation, such as fiber placement technology and robotic countersinking, introduced by BAE Systems. In Phase 3 of the digital thread transformation, the focus shifts towards providing mechanics with direct access to engineering data to create work instruction graphics. These graphics are instrumental in visually guiding mechanics on the factory floor or maintainers in the field, aiming to reduce the time required for task comprehension. However, in practice, maintaining these graphics on the factory floor proved challenging because they are static images, making it costly and cumbersome to update them as engineering or manufacturing changes occurred. The F-35 program with its concurrent engineering and manufacturing development, necessitated frequent updates to accommodate evolving processes, tooling, and planning. The impact of float-attack manufacturing on graphics creation was unexpected. As production rates changed, new tool positions were added, and hours per unit decreased, requiring constant adjustments to manufacturing sequencing and graphics. To address the limitations of static graphics, mechanics were granted access to visualization tools from their work terminals, allowing them to view instructions and harness installations on large television monitors. While mechanics typically require graphics for a short time, they are valuable for those new to the F-35 program during the ramp-up to full-rate production. Movies of critical installations have also been produced for access through electronic work instruction terminals. Optical projection technology offers a unique way for mechanics to utilize the digital thread by visually projecting work instructions onto the aircraft, simplifying tasks like identifying fastener locations and part numbers. Lockheed Martin is also working on capturing actual fastener grip data during automated drilling operations to enhance efficiency and support fastener projection. Another example of Phase 3 implementation is laser ply projection in the composites shop, which streamlines bulkhead marking and reduces costs. Additionally, additive manufacturing, such as fused deposition modeling, FDM of polymers, has been leveraged to produce over 5,000 tools for mechanics and sustainment modifications. Ongoing efforts aim to develop more durable FDM materials to replace traditional, more expensive tooling materials. Phase 4 of the digital thread involves the validation of the as-designed engineering data against the as-built structure through advanced non-contact metrology techniques, like laser scanning and structured light. This innovative technology is capable of early identification of deviations from engineering specifications during the manufacturing process, enabling rapid corrections and preventing defects from propagating downstream. It represents a potentially revolutionary advancement, with the potential to replace coordinate measuring machine inspections and potentially become a mandatory step for suppliers before shipping parts, tools, and equipment. Now, laser scanning can swiftly compare the as-built aircraft to engineering models in just a few hours. Another application involves troubleshooting fit issues with tubes on the factory floor. The cause of the problem might not be immediately obvious, whether it's a faulty tube, incorrect bracket placement, or a structural issue. To address this, the tube can be quickly validated using a scanner, or equipment can be brought to the aircraft to inspect brackets and structure. Current scanning methods often require the placement of targets on aircraft or parts, but feature-based recognition is expected to replace this approach as digital thread integration with 3D scanner technology advances. Moreover, this scanning technology has the potential to replace numerous manual measurements, such as mismatch, gap, and flushness checks, streamlining and enhancing the quality control process in aircraft manufacturing. That's a wrap for today's video. If you found this peek into aerospace manufacturing intriguing, be sure to hit that subscribe and like button. Stay tuned for more exciting content. Thanks for watching.